The RPM is so crazy that just the centrifugal force wants to expand the rotor, and it can accelerate a 2-ton car to 60 miles an hour in 2 seconds.
Many people who follow electric cars know the race has always been about range, speed, and charging time. But not everyone knows that something shocking may have just changed everything inside Tesla. A new engine linked to Elon Musk is now causing major attention, with reports suggesting it could reset the entire EV industry in one move. For years, companies fought the same battle until this moment arrived. So, what is this engine? And why are experts saying it may have ended the electric vehicle race without warning? Evolution of EV cars. The electric vehicle race did not start with Tesla. That idea is a myth that needs to be cleared up. In the year 1996, General Motors released the EV1 and placed it on the roads in California. It was not sold, but leased to customers, and many drivers liked it. However, GM later took back every single EV1 and destroyed them all. If someone wants a deeply unsettling story to explore, the history of the EV1 and its drivers is often mentioned. The modern era of electric vehicles began to form in the early 2000s when battery technology started to improve quickly. Lithium-ion batteries, first developed for consumer electronics, became the key technology for the industry. They were light, rechargeable, and able to store a lot of energy. Car companies began investing heavily in the same basic design, filling vehicles with many lithium-ion cells, controlling them with advanced software, and steadily improving range and charging speed with each new version. Tesla pushed this development much faster than others expected. In 2008, the Roadster showed that electric cars could be fast and desirable, not slow or unattractive. In 2012, the Model S showed that long driving range was possible, reducing the fear of running out of charge. By 2020, nearly every major car company, including Volkswagen, Ford, General Motors, Toyota, and Mercedes-Benz, had committed to building electric vehicles. The competition focused on the same goals: larger battery capacity measured in kilowatt-hours, better heat control, faster charging, and lower cost. For about 20 years, companies followed this path without questioning it. Most of the money in the industry went into improving the same system rather than changing it. The focus was on making existing battery technology better, not replacing it. Over time, this created a belief that progress would continue in the same direction indefinitely. However, incremental improvement has limits. By the early 2020s, it became clear that lithium-ion batteries were approaching those limits. One key limit is energy density, which is how much energy a battery can store for its weight. Improvements in this area had been steady, especially in the 2010s, but in the 2020s, the gains became smaller and harder to achieve. The chemical structure of lithium-ion batteries sets physical boundaries that cannot be removed just by better software or production methods. At some point, improvements become minor adjustments rather than real breakthroughs. Charging speed also has limits. Fast charging works by pushing large amounts of electricity into a battery in a short time. This process creates heat, and heat damages the internal chemistry of the battery. Over time, repeated fast charging reduces capacity. A battery that once offered 400 miles of range can slowly drop to 350 miles, then 300 miles. Many owners do not notice this decline until it has already become significant. There is also the issue of supply chains. Lithium-ion batteries require materials such as lithium, cobalt, nickel, manganese, and rare earth elements. These materials are not evenly distributed across the world. A large portion of cobalt, over 70%, comes from the Democratic Republic of the Congo, and much of the processing of rare earth materials takes place in China. This means the electric vehicle industry, which was meant to reduce dependence on fossil fuels, ended up relying on another set of tightly controlled and sometimes unstable global supply chains. So, when did Tesla start this move? Is it about efficiency in future transportation? Let's find out. SpaceX Tesla Tech Innovation. In 2024, information began to surface from engineering teams working at SpaceX and Tesla about a new propulsion and energy conversion system that had been under development for several years, mostly outside public attention and away from mainstream reporting. At first, most of the discussion in the media focused on familiar improvements in Tesla's existing electric vehicle technology. These included better battery chemistry, improved thermal management systems that help control heat more effectively, and updated manufacturing techniques being used at Tesla's Gigafactory production sites. These developments were real, and they represented steady progress in electric vehicle engineering. However, while these well-known upgrades were being widely reported, a more significant set of ideas was quietly appearing in technical documents, engineering papers, and specialist presentations that were only shared with small groups of experts during live streams and closed technical briefings. Within these more technical materials, there were references to a fundamentally different approach to how energy systems could be designed. This was not simply about improving existing electric vehicle architecture. Instead, it suggested a shift toward a new structure that could potentially replace parts of the traditional system entirely. The foundation of this approach comes from engineering principles developed in SpaceX's Raptor rocket engine program. The Raptor engine, which powers the Starship launch system, is built around a full-flow staged combustion cycle. This is one of the most advanced and efficient methods of chemical propulsion ever developed. For decades, it was considered almost impossible to implement in a working engine because of the extreme pressures, temperatures, and engineering precision required. Only a partial version of this concept had ever been achieved in the 1960s, and after that, it remained largely theoretical for more than 50 years. SpaceX eventually succeeded in turning the concept into a fully functional engine, not just once, but repeatedly. They built multiple versions, tested them extensively, experienced controlled failures during development, and gradually refined the design into a reliable, high-performance system capable of repeated launches. What is important in the context of Tesla's work is not the physical rocket engine itself. It is not possible, nor practical, to install rocket propulsion hardware inside a passenger vehicle. Instead, what is being transferred is the underlying thermodynamic and systems engineering philosophy that made the Raptor engine successful. This philosophy focuses on how energy can be processed in multiple optimized stages rather than in a single direct conversion step in order to maximize efficiency and reduce waste. In electric vehicle systems, energy efficiency is already relatively high when compared to traditional combustion engines. A typical gasoline engine converts only about 30% of the fuel's energy into actual movement, with the remaining energy lost primarily as heat and friction. In contrast, electric motors can reach efficiencies above 90% under ideal laboratory conditions. However, these ideal conditions rarely reflect real-world driving behavior. Everyday conditions such as traffic congestion with frequent stopping and starting, sustained highway speeds, cold weather that affects battery performance, steep inclines, and rapid acceleration demands all contribute to noticeable drops in overall efficiency. In response to these challenges, modern electric vehicles rely on complex energy management systems that constantly adjust power delivery. While effective, these systems also introduce additional layers of computation, hardware complexity, weight, and small but cumulative energy losses. The proposed new architecture changes the way electrical energy is processed and delivered to the motor. Instead of converting energy from the battery into rotational force in a single continuous step, the system divides the process into multiple distinct stages of energy conversion. Each stage is designed to operate within its own optimal efficiency range, rather than forcing one system to handle all conditions at once. Energy that would normally be lost as heat during each stage is not simply discarded. Instead, it is captured, redirected, and fed into the next stage of the conversion process. This creates a continuous loop of energy refinement, where each step improves the quality and usability of the energy being delivered to the drivetrain. The core idea behind this approach mirrors the same engineering principle that made the Raptor engine significant: minimizing wasted energy at every stage of conversion, and ensuring that as much usable energy as possible is preserved and reused within the system. In this framework, heat and other byproducts of inefficiency are treated not as unavoidable losses, but as recoverable resources within the energy cycle. However, preliminary internal testing of this system, according to reports discussed in engineering circles over recent months without widespread media coverage, indicates that real-world driving efficiency could improve by approximately 30 to 40% compared to the most advanced electric motor systems currently in production. But is 30 to 40% an impressive figure? What's the science behind the engine? Let's find out. EV efficiency and weight. A 30% improvement in electric propulsion efficiency does not mean electric cars become 30% faster. That is not how the system works. It means that the same stored energy can now be turned into 30% more useful output. In practical terms, if you want to keep the same driving range, you would need about 30% less battery capacity to achieve it. This immediately changes several things. A smaller battery means the vehicle becomes lighter. A lighter vehicle is also cheaper to build. It also reduces the need for large quantities of materials like cobalt, lithium, nickel, and manganese, which are already difficult for the industry to source at scale. Instead of trying to fix supply shortages by securing more mining agreements or negotiating harder with countries like the Democratic Republic of the Congo, the problem is reduced by simply needing less raw material in the first place. But the impact goes even deeper than supply chains. Weight plays a major role in electric vehicles in a way that is not always obvious. Battery packs are extremely heavy, often ranging from about 400 kilograms to 900 kilograms, which is roughly 800 to 2,000 pounds. This is a large mass that the electric motor must continuously move along with the rest of the vehicle. Moving that weight requires energy, and that energy must come from the battery itself. But using more energy means the battery drains faster, which then requires either a larger battery or reduced range. This creates a feedback loop, sometimes called a mass spiral. Adding more battery increases weight. More weight increases energy demand. Higher energy demand requires even more battery. This cycle creates diminishing returns, where each added kilogram of battery contributes less and less improvement in driving range because part of the gain is used up just carrying the extra mass. A 30% to 40% gain in efficiency disrupts this cycle. If fewer battery cells are needed, the pack becomes lighter. A lighter pack reduces the energy required for motion. That lower energy demand can then justify an even smaller battery, which reduces weight again. Instead of a self-reinforcing problem, the system begins to reinforce itself in the opposite direction, creating a positive feedback loop where improvements build on each other. In engineering terms, such reinforcing cycles can grow in powerful and sometimes unpredictable ways when systems are redesigned at a fundamental level. A useful comparison is the full-flow stage combustion cycle used in advanced rocket engines. It works because it pushes energy conversion closer to theoretical limits defined by physics, not by making small adjustments, but by redesigning how energy moves through the system and how waste energy is reused. The efficiency gains are structural rather than incremental. When a similar kind of architectural change is applied to electric motor systems, it does not simply improve existing designs. It replaces the underlying way energy is converted and used. Early results already suggest efficiency improvements of around 30% to 40% compared to conventional systems. But the key uncertainty is not whether it works at this stage. The early evidence suggests that it does. The real question is how far it can ultimately be pushed. Like early versions of advanced rocket engines that continued to improve with real-world use and refinement, this type of motor architecture is still in its early stages. The first implementations are already showing significant gains, but they are unlikely to represent the final limit. However, what remains unknown is the upper boundary of its performance, and that is something only a small number of engineers working directly with the system currently have any real visibility into. How's the industry reacting to the development? Is there some kind of anxiety? Let's take a closer look. Unusual silence. Inside the automotive industry, the reactions from engineers and people in the car industry have been, and this needs to be chosen carefully, revealing. Not loud, not dismissive, and not the kind of public argument you would expect if experts strongly believed a claim was false. Instead, the response has been quiet, careful, and in some cases noticeably slow. When Tesla shared earlier breakthroughs, competitors reacted quickly and with confidence. For example, when the 4680 battery cell was announced in 2020, battery experts from rival companies immediately began analyzing it. The structural battery pack design also received sharp technical criticism within a short time. At that time, the industry clearly understood what to examine and quickly formed opinions. But the reaction to the new staged combustion motor design has been very different. Some well-known experts in electric motor engineering have not published anything at all. Others have made very short and carefully written comments in industry journals, simply acknowledging the technology exists, but refusing to evaluate it for now. One senior engineer from a major European car company, speaking anonymously to a technical publication, said the design needs more study before any judgment can be made. More study is a very important phrase here. Experts usually do not say this about ideas they already believe are wrong. They say it when they are still trying to fully understand something. Some academic researchers in thermodynamics and motor engineering have spoken more openly in private discussions shared within engineering circles. According to those discussions, the general view among the small group who have reviewed the technical details is that the theory behind the design appears solid, the efficiency claims seem possible based on the structure, and the main questions are about whether it can be manufactured at large scale and whether it will remain reliable over long-term real-world use. These are assessments coming from people whose work is normally based on skepticism toward bold claims, yet the most striking part may be the silence from major car companies. Volkswagen has not responded. Toyota's hydrogen fuel cell division has made no statement. General Motors, which has invested heavily in its Ultium battery system, has not commented. Ford has also remained silent despite ongoing challenges in its EV programs. When established companies stay quiet about a possible disruption, it usually means one of two things. Either they have studied it and decided it is not important, or they have studied it and are deeply concerned. But the way they are behaving does not strongly suggest the first option. Who stands to lose if this technology actually performs the way early data indicates it might? Could it be the traditional automotive industry? Let's find out. Industries that could collapse from EV breakthroughs. Car manufacturers that have invested tens of billions of dollars into lithium-ion battery technology are now facing a very difficult situation. However, traditional car companies may not be the ones facing the greatest danger. Many of these companies already understood that the battery systems they were using were probably not the final solution for electric vehicles. Because of this, they created research departments, studied new technologies, and closely watched changes happening in the industry. They still have other choices available, even though changing direction would cost huge amounts of money and create serious challenges. The industry facing the biggest risk right now is lithium mining. Companies invested huge amounts of money into mining projects in countries such as Australia, Chile, Argentina, and areas like Nevada. Now those predictions no longer look as certain as they once did. Many of the financial forecasts created by analysts and companies are starting to appear less reliable, and the people who made them are probably hoping they will not be examined too closely anytime soon. If a new technology improves electric vehicle efficiency by around 30% to 40%, and that means each vehicle needs 30% fewer battery cells, the effects could be enormous. It would not simply slow down the growth in lithium demand. This creates serious problems for mining projects that were funded based on the expectation that lithium prices would continue rising because of endless demand growth. If the demand curve begins moving in the opposite direction, many projects that once looked highly profitable may suddenly appear risky and financially unstable. The cobalt industry could face an even bigger problem. Cobalt has long been one of the most troubling parts of the electric vehicle supply chain. It is expensive, difficult to obtain, and heavily concentrated in politically unstable regions. Mining operations connected to cobalt production have also faced major criticism because of poor working conditions and ethical concerns. For years, battery manufacturers have been trying to reduce the amount of cobalt used in batteries, and they have achieved some progress. A technology that lowers the total battery size by 30% would help reduce cobalt use, but it would not completely solve the issue. However, a technology that eventually replaces lithium-ion batteries altogether could change the entire situation completely. Another industry that may be affected is charging infrastructure. Companies and governments have spent billions of dollars building fast charging networks based on a specific understanding of how electric vehicles operate. These systems were designed around long charging stops, powerful charging stations, and large charging networks placed along major travel routes. Then there is the oil industry, which has been quietly observing the growth of electric vehicles very carefully. Major oil companies understand that electric transportation could eventually threaten the foundation of their business. Because of this, they have spent years studying how quickly electric vehicles might spread around the world. So, what do you think about Elon Musk's new engine that may end the EV race? Share your thoughts with us in the comments section. Don't forget to like and subscribe.